Welcome. This course covers evaluation and optimization of AI agents, from metrics and judges to cost, caching, and CI pipelines.
Agent evaluation is hard because multi-turn, non-deterministic loops need more than single-turn text scores.
The evaluation pyramid rises from unit components to trajectories to end-to-end task success.
Use exact matches where possible, and fuzzy semantic or trajectory scoring where answers vary.
Core metrics include task success rate, trajectory efficiency, tool call accuracy, and cost per task.
Ground truth is hard. Synthetic sets scale, while real user gold standards capture production reality.
Offline evals protect before deploy. Online monitoring watches live telemetry after release.
Shift-left testing moves evaluation into developer pull requests and CI workflows before production.
Section 1 takeaways: evaluate units, trajectories, and tasks. Use behavioral metrics and protect production with offline evals.
Pause here. Final text alone is not enough. Measure the whole loop. Now the quick check.
Quick check after Section 1. What is the primary advantage of evaluating agent trajectories over just final text outputs? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 2 focuses on trajectory and tool call evaluation across the full agent path.
A trajectory is the step-by-step path from state through actions and observations to the final output.
Tool call accuracy checks tool name, argument syntax, and parameter validity against API specs.
Trajectory efficiency compares an optimal short path with wasteful long loops that add cost without value.
Redundant or hallucinated tool calls, such as repeating the same database query, are important failure signals.
Parameter inspectors catch missing required JSON keys before a bad call hits the API.
Error recovery evals test whether the agent recovers gracefully when a tool returns a server error.
Step-level attribution isolates whether failure came from planning, tool syntax, or another node.
Section 2 takeaways: score tools and schemas, measure efficiency, and isolate failures to specific nodes. Pause here.
Pause here. Paths reveal hidden waste, and attribution speeds debugging. Now the quick check.
Quick check after Section 2. What should trajectory efficiency evaluation primarily detect? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 3 covers LLM as a judge patterns, bias mitigation, and agent benchmarks. LLM as a judge uses a strong frontier model to grade lower-cost worker outputs against strict rubrics.
Robust rubrics use clear 1 to 5 scales for accuracy, completeness, and groundedness. Mitigate judge biases such as position bias, verbosity bias, and self-enhancement bias.
Pairwise comparison asks the judge which output wins, loses, or ties in a head-to-head match.
Industry benchmarks include SW Bench, Gaia, and Web Arena for different agent skills.
Also build domain-specific suites with dozens of realistic internal cases that mirror production edges.
Calibrate LLM judges against human experts, for example with Cohen's Kappa agreement scores. Section 3 takeaways. Judges scale nuanced eval, rubrics reduce bias, and benchmarks set real-world baselines.
Pause here. Judges need rubrics and calibration, and benchmarks set the floor. Now the quick check.
Quick check after Section 3. Which problem occurs when an LLM judge favors longer answers regardless of accuracy? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 4 covers prompt and system optimization with programmatic compilers such as DSPY. Handcrafted spaghetti prompts break when models or schemas change, so manual tuning does not scale. Frameworks such as DSPY treat prompts as declarative modules that can be compiled and optimized. Optimizers can select high-performing past trajectories as dynamic few-shot examples.
Instruction Bootstrap Tuning tests many system prompt variants and keeps the highest scoring candidate. Distillation collects successful large model traces and fine-tunes a lightweight model on them.
Tool description optimization rewrites docstrings from error traces, so models choose tools more correctly.
A continuous loop recompiles prompt instructions whenever eval scores fall below baseline.
Section 4 takeaways. Replace manual hacking, compile instructions in few shots, and distill into smaller models.
Pause here. Optimize programs, not paragraphs, and let evals drive the compiler. Now the quick check. Quick check after Section 4. What role does DSPY play in agent system optimization? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 5 covers latency, cost, and caching strategies for production agents. Latency includes time to first token, tool execution time, and iteration overhead across the loop.
Cost drivers include input token bloat, expensive reasoning models, and redundant subtask calls. Semantic prompt caching stores and reuses identical system prompts and tool schemas.
Tool caches reuse deterministic results for identical parameter calls, such as repeated GET requests. Model tiering routes simple steps to small models and reserves large models for complex reasoning. Token budget guardrails terminate runaway loops before they exceed a preset spend threshold. The ROI frontier
is the sweet spot between latency, accuracy, and per-task token budget. Section 5 takeaways. Cache and parallelize for latency. Route simple steps cheaply and enforce hard token budgets. Pause here. Cost is an architecture choice, and caches plus routing compound savings. Now the quick check. Quick check after Section 5. How does model tiering optimize production agent costs? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 6 covers observability, tracing, online evals, and agent CI/CD pipelines. OpenTelemetry standardizes spans, events, inputs, and outputs across every node execution.
Trace trees show step duration and token counts across platforms such as Langsmith, Phoenix, or Arise.
Production alerts fire on sudden spikes in loop counts or tool exception rates. Online evals sample production traces through judges to track quality drift in real time. An agent CI pipeline runs unit tests, trajectory evals, and cost simulation before deployment. Canary deployments route a fraction of traffic to a new agent version and compare success rates. A data flywheel turns failed production traces into new annotated regression test cases. Section 6 takeaways. Trace deeply with OpenTelemetry, run online evals for drift, and gate deploys with CI regressions. Pause here. Visibility makes quality manageable, and CI turns evals into gates. Now the final section check.
Quick check after Section 6. Why is OpenTelemetry integration essential for production agent observability? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
You completed a quick check after every section. You can now evaluate, optimize, and observe agents before and after deployment. Congratulations! You completed evaluation and optimization of AI agents. Thanks for watching.